We have only one talk here with Alex Hubbard, who is going to be talking about fratricidal dynamos. So please, Alex.
Okay. Well, this picture is actually not chosen because I think it's late on a Wednesday and you were all asleep. This picture is chosen because it became clear to me that the word fratricidal is actually not commonly understood. It's based on cidal. It's the same side that exists in suicide or homicide, i.e. killing, and frat for brother. It is the killing of a brother. And the picture is in homage to nuclear fratricide, which is at least a theoretical phenomenon where the first nuclear warhead to arrive destroys the subsequent ones before they can explode. Which is actually the context in which I think first learned the word. So, originally actually scheduled to talk about magnetic helicity fluxes in sharing systems. And early on in that project, where we were going to look for Vishnack-Pinchot flux, I was running an alpha-omega dynamo in a shared sheet. And sort of launched one, looked at it after a short time, saw a dynamo wave starting, a field that looks like an alpha-omega field. So I was happy and decided to continue it to try to get actual statistics on fluxes of helicity. Studied it significantly, still looked like an alpha-omega, and then I went on vacation. And rather than trying to come up with an intelligent new run to run, I just extended this run because I had nothing else to do. And this is what happened. At some point, about 8.5 or 9 equivalent times later, the alpha-omega field vanished. Here it is after the event. So we wrote up the helicity flux information. We did not actually find any Vishnack-Pinchot flux. And then we decided to look at this in something more detail. So I will be talking about this in the language of mean field theory, which is how we can characterize dynamo modes. All of this, I think, is old hat to all of you, with the possible exception of noting that our shear is always a y-directed velocity depending on x. And we will always be running in shearing periodic setup. So our system is a cube. It is strictly periodic, except for the shear velocity itself. And as a further note, everything we'll be talking about is fundamentally a nonlinear process, and as such, some of this theory I'll be developing is linear and can really be looked at as more qualitative than quantitative. So if you try to do mean field theory in a sharing sheet, you get at least for many of us, a fairly familiar eigenvalue problem. So assume you have a mode that actually will take only to vary along x and z. It has no variation in the toroidal direction. And there are two key solutions. The one that varies along z, which in this case is our alpha-omega mode, and the mode which varies along x, which does not feel the shear at all, and is a standard alpha-squared mode. The superscripts refer to the direction of the field variation. I'll be using planar averaging. So the superscript z means I'm averaging over the xy plane. I'm getting the field that varies as a function of z. Similarly for the yz averaging. This captures, in this case, the alpha-omega mode, and there the alpha-squared mode, but also captures anything else that occurs with that variation. So when you calculate the growth rate, this growth rate for the two modes at equal k is greater for the alpha-omega mode, and therefore we expect the alpha-omega mode to dominate. So here's a run. The endpoint here is actually where I stopped extending the run. And and we see a clear traveling alpha omega wave. The Z varying field is significantly stronger than the X varying field. But, as noted before, that doesn't always exactly happen. So here we actually get the first picture of what might have happened in the run I described earlier. The Z varying field vanishes, and the X varying field takes over. Now, before the transition, we have an alpha omega mode varying along Z, and the X varying field doesn't really look like much of anything. Whereas after the transition, the alpha omega mode has completely vanished. There's no signal there. But we have something that looks like a slightly distorted alpha squared field. A pure alpha squared field would have the same amplitude there. But that, I think, is going to recover at a later time. One of the ways we try to look at this was the idea of interactive modes. So if we take an alpha omega mode, and we also put in the same system a slightly distorted alpha squared mode, the H there and the G there are parameters which determine how much stronger the toroidal field is compared to the colloidal component. Then it turns out that the Lorentz force can be written as a force that varies, is directed along y and varies as both a function of x and z with k1 and a potential component. As we're operating in an approximately incompressible regime, we proceed to just drop that term. Now, as you can imagine, you have a force like this, which varies to cosine x and cosine z. Then, if you have a dominantly alpha omega mode, for example, and you have it interact with this with a flow that's developed by this, then there will be a finite z average, and all of a sudden you'll have x variation. And that could be one way to go from a z varying alpha omega field to an x varying alpha squared. So if you imagine that there's some sort of parameter parameterizing the amplitude of the velocity flow that develops, then you can go into the mean field theory. There's a parameter I. There's no real reason to get the actual formula for it here. It's based on U. And it forces the growth of the alpha squared mode. It actually reinforces the alpha squared. And if we have a saturated alpha omega mode, so this is the growth rate of the alpha omega mode. If it's saturated, this is about 0. If I is comparable to the shear, then even in the nonlinear case, the alpha squared mode could grow in the presence of a saturated alpha omega mode. So here's a run where we think this is happening. Here's the z varying alpha omega, the x varying alpha squared. We see here it is in fact sort of a traveling mode wave associated with the alpha omega. And here, well, it probably looks like sort of like an alpha squared in the x varying field. We do in fact see that velocity field. So here's sort of the quadrupolar geometry of the velocity flow. This is flow along y. But this picture doesn't actually work for us entirely, because it's a picture of instability. It's a statement that the alpha squared mode in this parameter regime where this happens is in fact unstable. So the alpha omega is unstable to the growth of an alpha squared mode. So it's not surprising this happened very, very early in the simulation, because as soon as you grow your alpha omega mode, well, the alpha squared is going to be excited, it's going to be left over from the kinematic phase, and it will grow. So there's no way here to really have a long-lasting alpha omega mode. So going back to the run I showed you, the first way I looked at this, I went back to sometime just before the transition, and I launched 2 runs taken from that data. Due to a minor technical fill-up, the random seed, and only the random seed, got changed. And the time of transition changed. So this one is transition about 8.5, next one maybe 9, and then one at about 10. I also went back a lot farther, also changed the seed, and got a transition at maybe 11. Now, 9 to 11 turbulent resistive times That's actually, so that's to this sort of this difference of maybe 2 or 3 resistive times. There's actually a difference of something like 1,000 to 2,000 turbulent times. But still, maybe there's something deterministic, something slow, steady happening in the background, presumably resistive. It's actually setting that there will be a transition around here. However, in a slightly different run, or set of runs, all these were done with different C's starting from the time of 0. I got one transition at 5 and another transition at 21 resistive times. And you can multiply those by something like 700 or 800 to get turbulent times. So it really does not look like this right here. There's some steady process happening in the background that sets a transition time. We believe that this is actually a random process due to the forcing. Some detail in the forcing. But can we use the previous picture to explain what's going on? That looks slightly risky. When we looked at the heuristic plots, the transition took something like 3 resistive times. Here it's taking maybe half a resistive time. But mainly you should think that this system appears, the alpha omega mode appears to be stable. So even if the system could temporarily be kicked through some portions and some details in the forcing into an unstable mode, that unstable mode would have to self-support itself, or the random turbulence, again, this takes hundreds of turbulent turnover times for this transition, would reassert itself. So clearly there's something going on that's reinforcing the transition, but it would not be surprising to us if that previously discussed instability actually is not occurring. So this is one case I looked into a lot more detail. So we see the alpha omega mode going to the transition at 25.5 there. And the bottom, we see the x varying alpha squared mode, or not actually alpha squared mode that shows up. You see, at the time when the alpha omega mode is gone, the toroidal component of the x varying field exists, but the colloidal field of the x varying component has not yet shown up. We don't actually have a straight transition to an alpha squared. In fact, this right here just appears to be the alpha effect creating a field from this. Going into slightly more detail, here's the equivalent velocity plot taken about here. When we don't see any of that sort of ordered polar flow structure. This is actually taken from the plot which did see that steady instability. And so you see fairly steady action. If I take a similar plot for this one, well, the y-varying field is acting fairly aggressively. The toroidal component of the z-varying field is slowly varying a bit there. But I don't see any actual particular relationship between these plots. So we're pretty sure that the second transition does not occur in the same fashion as the first. It's not necessarily surprising, since the first one just appears to be a case that in some parameter regime, the alpha omega mode is unstable to the growth of an alpha squared, whereas in another regime, something happens, and then we go from a stable alpha squared mode, we get kicked into a Price and parameter space where we'll inevitably end up in an alpha squared, and that happens in a very different fashion. So we tried to figure out how that happened. We're looking at correlators of helicities, since as people have been discussing in great detail, helicities are quite important to alpha dynamos. Magnetic helicity, the current helicity, and the flow helicity. But there's no actual structure that we can particularly see there. We also went into greater detail looking at using the tensor method to pull out alpha coefficients. In particular, we're picking up coefficients that actually have spatial variation both in x and c. The idea is going back again to this velocity idea. If the alpha coefficient is k is equal to 1 in x and k is equal to 1 in z, then it can translate an x-varying field into a z-varying EMF, or a z-varying field into an x-varying EMF. Here, they're just there's 27 coefficients here. I don't think I could show 27 coefficients usefully. I only picked out the coefficients that create the EMF that would create the toroidal field that was the first to develop. Unfortunately, the data is quite noisy. The signal is a fairly short signal in many ways. And due to the details of the test yield method, we cannot actually get out too much information there. So basically, the picture here is one that we don't see anything obvious explaining why our alpha omega is turning into an alpha squared. I think that's the next one anyways. In terms of parameter space, the parameters that we ran this over, well, here, red diamonds are runs which I simply stopped running at some point. They stayed alpha omega for the entire run. The size of the diamond says how long I ran that. The squares are runs that transition in the random fashion. The size, again, says when the transition occurred. Circles are completely different. They even show up here. Okay, if you manage to see the circles, more power to you. They're on a completely different scale. Those are runs which never actually entered an stable alpha omega mode at all. I haven't talked about that, but sometimes these systems are exiting the kinematic phase and basically going straight into an alpha squared. That happened once here, twice there, and 3 times in that case. But mainly, I'm looking at this, and I don't see very much spatial information. I can't guarantee that this run right here is even the alpha squared number is even excitable. It would be excitable if there was no shear, but its excitation conditions for an alpha squared dynamo in the presence of shear are not well known. All of the deterministic cases were here, and below that, the shear turned out to be basically a perturbative effect and didn't really control anything. Another question that shows up, of course, would be reverse transitions. What I can say there is we haven't seen any. It doesn't mean it doesn't happen. But the fluctuation suggests that it won't. In the deterministic instability case, we, of course, don't expect any transitions. It's just actual instability that drives you towards an alpha squared. But even there, we can see that here, there's a lot of fluctuations in here. Those fluctuations have mostly gone away. And that is even more pronounced in this run. Huge fluctuations, tiny, tiny fluctuations. So I'm not expecting any reverse transitions. What this is, again, is Cartesian triplet periodic sharing sheet. That could change if you go to another geometry. So conclusion, nonlinear behavior can be surprising. We have already seen suicidal dynamos which turn the flow into flow which no longer support final action. Here we have dynamos which turn from one mode to another. And long-term alpha omega modes may not actually exist. If this result generalizes to more geometries, if reverse transitions do of course exist, then this becomes a possible explanation for things like the Maunder minimum. But again, we're a slight problem that it's expensive to run simulation for a very long time, and if we have random, unpredictable transitions between modes, then we have to run simulations for a long time to get a good guess of what will actually end up. And pretty much that's it.
So, do we have any questions?
It's very interesting. I think you have what the dynamical systems people call a blowout application. And so your first attractor, your alpha omega attractor, has what they call a riddle basin of attraction. And what that means is you go into some chaotic attractor, you wander around it for a while, and then eventually what they call a transversely aponomic exponent becomes positive, and you get booted out of that attractor, and then you've gone to some other state, the alpha squared state. And there's been a lot of work.
It's clear that something in that language is happening,
Right.
at least in the non-deterministic case.
So there's been a lot of work looking at transition times from attractors to see whether you can tell whether it's this deterministic or whether it's random. So I know they're really expensive calculations.
Well, these I have to admit, my resolutions are not very high because I was just having to run vast numbers of simulations for long times. And anytime I run a simulation, if nothing happens, of course, I can't say that nothing will happen in the next extension. But yeah, there's definitely a lot more work to be done there. If I could explain this, I would have published a lot earlier, but sort of right now, this is the publish this now and look at it again later state.
Steve, would simple Lyapunov point array map be a good diagnostics?
Yeah. Well, it would be one of the diagnostics. You have to work out where in phase space your attractors lie, which is fine.
Yeah, the real thing is if we can come up with a good way to deal with these large fluctuations, I feel a lot happier. Right now, those fluctuations are simply so large that it's not clear to me how well we can do anything.
You're going to find it almost impossible to come up with a physical reason why at some stage you get booted out. Of course I am, because it's an incredibly rare event in terms of turbulent forcing issues. But if you can reconstruct the attractor, you might be able to say, when we come to this part of the attractor, that's when we get booted out.
Yeah.
Alexander, do you study behavior of helicity, say kinetic helicity or magnetic helicity in presence, or if you like, current helicity during this transition?
A little. There's this. I'll admit here that the actual temporal resolution here is pretty poor because helicity is a painful thing for me to get easily from pencil code. The test field method effectively is a measure of kinetic helicity. So this right here is the best measure of kinetic helicity that I have. But again, it is not actually a very good one. So the kinetic helicity with respect to actually doing stuff with the magnetic field. But it has actually a lot of problems associated with it.
Can you answer in general? Something happened visible?
If it's anything more visible than what I've shown happened that I saw, I would have presented it.
Let's hope for the best.
Okay, any more questions?
How about the magnitude of current helicity and kinetic helicity? If the magnitudes are very similar, the residual may change its size or something. Even if each profile is not so.
The amount basically follows. The amount basically follows the field strength. Although I have to be careful here because alpha omega fields are significantly subhelical, which is part of the reason why I think this is happening. Alpha omega fields, if you look at the solutions, there's 1 over alphas that show up, and the alpha actually is much more strongly quenched. So fluctuations can actually change the sign. Might be able to change the sign of alpha temporarily for a very brief time. So the alpha does get a lot more quenched here because of shear, and alpha it can support the dynamo against much weaker alpha effects.
Okay, so if there's no further questions, let's thank Alex again. And then we have about an hour more discussions. Before the conference, Axel and Igor asked if I would entertain the audience for an hour, but I don't think that my comedian skills are that good. So, no, I'm not going to sing.
You don't know enough to finish singing freaking songs?
But there has been one method which has which keeps popping up in many talks, and it's kind of fitting that Karl-Heinz is the intellectual father of this method. And we are, of course, talking about the test field method. And Axel, we're doing some statistics on the talks, how many talks actually mentioned the test field method.
10 out of 29 so far.
Okay, so this is fairly substantial. So maybe this could serve as our starting point for discussion. So the test field method is about 5-6 years old, and now it seems that it's fairly established in terms of people using it. And not so much criticism as in the beginning is appearing any longer. But then Matthias also presented lots of new varieties of test field methods. And those may not be so well discovered or so well studied yet. And one interesting point would be to compute also the lambda effect and turbulent viscosity using similar methods. And
To jump in,
Yes.
Matthias repeatedly asked the question whether the non-locality played a role, whether you could just have your coefficient as a function of space, or whether you needed this k-dependence. So maybe that would be a good starting point for the discussion.
It was exactly the question. So maybe I should say that space dependence and non-locality is not the same in the coefficients. There might well be a homogeneous situation where they nevertheless depend on scales, or k-dependent, and the EMF is then non-locally connected to the mean field. And in addition, there might be an inhomogeneity which makes the coefficients, in addition, say z-dependent. This is what Piadi has shown, for instance. And again, in this case, the test field method seems to work out the coefficients correctly, insofar the mean field, the mean EMF could be reconstructed satisfactorily. Okay, is it what you want to do? Okay, not only matter. I want to propose a question too, maybe. It would be helpful in case that anybody has still some sort of skepticism, yes, or fundamentally questioning this sort of approach to the testing method, it would be uttered now. There should not be hesitation to do that. It would be extremely helpful.
Okay, so I'm from Leeds, so I kind of have to say something. David Hughes is not here, so I think I put my David Hughes head up and say, you assumed a lot when you gave your talk. You assumed things were linearly related to other things, because that's the only way you could do the test field method. And that, I think, has to be rigorously justified. I mean, it's all very well saying it looks okay, it seems to do a good job, but we know, let's forget about MHD, let's just look at the lambda effect or an Acker effect or whatever. We know that that equation is fundamentally non-linear, and the difficulties come from cascades, inverse cascades, whatever they are, Reynolds stresses. And so all the difficulties come from non-linear interactions. So David Hughes would say, not me, David Hughes would say, no, you have to show that it really is linear in the way that you assume.
Could I reply?
Yeah.
So,
Back to David Hughes.
well, maybe 2 points. So, with respect to the latter, the pure hydrodynamics and say turbulent viscosity and so on, effect. But what I have shown were results only for the kinematic case, intentionally, because others are not available at the moment. But I think in that case, there is no significant action of the mean flow onto the turbulence. I think this method is still well established, because the governing equations are in fact always not linear, you're right. But we have decomposed them exactly in two groups, one of which is nonlinear and it solves properly, and the other one is definitely linear. And this is only true, of course, if we have a kinematic case. That's why in this case I would be confident that the results are really well-founded. That's one remark, and the other is we are meanwhile using this term, the quasi-kinematic method, for the cases where we deal with the mean field coefficients for the mean electromotive force, and we have only a hydrodynamic background turbulence. And then we have to figure out these coefficients. We have to deal essentially only with the induction equation. But the induction equation is linear by itself. So in this case I would insist that even if we have a transit situation where the velocity field is already influenced by the mean field, then the method is nevertheless well-founded. So that I would be interested in, could you accept the letter?
Okay, formally, the induction equation is of course linear for a prescribed u. In the nonlinear regime, u is a function of bit. So you still have to be a bit careful. I mean, so to answer your question, then no, probably I wouldn't accept it. But no. But you know, that's me. I'm from Leeds. The place Cowling was very sceptical, so we all have to be very sceptical.
But mathematics is global, isn't it?
Yeah, but you can be a miserable bugger, which is what we're like in Leeds. You can be very miserable, which is what we're like in Leeds. We tend to be kind of negative.
If I might, could we come up with a possible test case? That will be interesting. When instead of saying what we accept and then debating about it, could we come up with quantitative measurement of what could be done, and then we test it and see if it works or not?
Well, I believe there was a paper by Alice Courvoisier and was it David Hughes and Mike Proctor, where they did some various cases using not the test field method, just solving equations. So that seems to me to be quite a good test case.
Didn't you refer to 2010 in first release of the Royal Society?
Yeah, that sounds kind of...
Maybe I can make a remark. Yeah. So we have addressed this paper in our publication of last year, and it's in fact so that their case, as they treat it, it can be interpreted in another way, but as they interpret it, it really refers to a case where the background consists both of a hydrodynamic and a magnetic turbulence. And we have never claimed that the quasi-kinematic method is correct in that case. Because it is not, we have developed the other one which I presented yesterday. And only a comparison to this method is really relevant. But
what you presented yesterday did not have the u dot grad u term. So formally, if you don't have that term, you can separate the u into a magnetic driven bit, and that's a bit different to when...
You're right. What I presented yesterday is even not yet sufficient. It needs to be extended or melted together with the hydro method. And then one could start to compare to the results of Courvoisier.
So that, I think, is a good idea.
Yeah.
Those equations, by the way, are in the appendix, and they have been programmed but not debugged completely. Maybe Matthias should maybe emphasize that when he talks about hydrodynamic background turbulence, that could actually include the case of zero flows. So the magnetic buoyancy instability is an example of that, where you would say there's zero, it's a purely velocity. I mean, there's no background. There's no hydromagnetic background, yes.
Not at all any background. It's without any background.
In this case, yes. So it's quite remarkable. And of course, Piali demonstrated that it actually works, but she had to go to the non-locality to make that really a waterproofed case.
I think if we accept idea that coefficient in the electromotive force in reality is a functional derivative of large-scale magnetic field, or a derivative of large-scale magnetic field, in this case I think we haven't any contradictions, because it's more or less the same that you say in Leeds. I haven't personally doubted David Hughes, very clever gentleman, it's true, But nevertheless, I think it's just question of terminology and nothing else. If it's true, of course, test field method or import field method, which you simple add infinitesimal small shift from real situation, why you cannot calculate this condition?
Because the equations are fundamentally non-linear.
But it is true, but you use, for example, Lyapunov exponents in order to describe nonlinearity.
Yeah, but you have to be very careful. If you're perturbing about chaotic state, it's not actually clear that there is a well-defined linear problem you can do.
It's similar to experiment. If you will not produce experiment, you will never get answer.
Yeah, but you'd quite like to get the right answer, wouldn't you?
Right now, the right question.
It's like the last talk we saw. Okay, there was a very, very complicated non-linear state. Every so often, you got booted out of that state to some other state. If you try to do some kind of average linear instability problem, which is what Alex was talking about, you wouldn't get the right answer. So you have to be a bit more careful.
Suppose you calculate your total nonlinear system in DNS for some level. After that, when you find all fields, you just put small perturbation and ignore any nonlinear phenomenon for this simple perturbation. It gives you total information of your derivatives.
No, not if the original system you're looking at is already chaotic. You can prove rigorously that there are super exponentially growing modes. That's
it's another story. It's another story.
Yeah, they're the fastest growing nodes. Look, they're
Again,
super exponential.
good question. Good answer. Go on.
That wasn't. I didn't say what I would do. I'm just saying we were discussing whether it makes sense to linearize about a complicated non-linear state. The answer is sometimes.
But if you have got functional derivative as function of real magnetic field, for example, it means you know all response of your electromotive force, say. You agree with the electromotive force is fundamental, how to say, value.
I do. I agree. I mean, that's one of the things I think. I think what we should be calculating is the electromotive force. But I don't quite know. I mean, I do know. Historically, what we do is we calculate the transport coefficients. But what's really of interest is the electromotive force.
Right.
So I agree with you. That's the fundamental.
All transport coefficients just a functional derivative of
The
electromotive
electromotive force is really well, as I said and as Karl Hanser said, it's an integral over all space and all time. I mean, it's really a differential equation satisfying.
Maybe.
So there's this integral where you need the correlations with other points in space and the memory effect in time. So.
Okay, I have a practical question. So if we consider numerical simulations in turbulent convection, so there is a problem with separation of scales. And in principle, results depends, turbulent transport coefficients depends on K. Of course, if you have forced turbulence with a good separation of scales, you choose your method for K equals 0. And now, if we work with a turbulent convection where there is no separation of scales, there is a problem with this, what is the practical recommendations? How is it possible to find transport coefficients? What we can take? K equals 0, K equals 1, or we should integrate over K. So what we can do?
So what could do two things. First, simply by brute force, figuring out the coefficients as functions of K. And if they start to convert to zero, or sorry, to a constant, or sorry, well, to zero, this actual behavior should go to zero somewhere.
They're not zero.
No, I mean, withdrawing K. if you increase k further and further and further and figure out all these values, and you see this curve goes to 0, so the last coefficients you see are already sufficiently small, then you might say this is enough. And another recipe would be to look for the mean field which is present in your setup. That's what the Piali has done. If you look at what are the constituents of the mean field in terms of spectral of k, spectral constituents, and then it was obviously only necessary to figure out the mean field coefficients up to the point to which one needs them, to dot them, so to say, into the B to get the median. So in her case it was so that indeed the mean field coefficients in most cases converge to 0 with growing k, with increasing k, but some did not in the region or in the range of k's she considered. But because at the same time the mean field was converging already to 0 with respect to k, this was nevertheless resulting in a convergent EMF representation.
Okay, this I understand. Just, okay. For example, we have turbulent coefficients. For example, we have turbulent coefficients up to the k equal 10. What we need to do in order to get final result, we would like to know what is the effective velocity. Do I need to integrate over k and find a physical answer for effective velocity? Yeah?
Yeah, there are two possibilities. Either you work two possibilities. Either you work in the k space.
Yes.
So you have a mean field model, say, where a mean field occurs, and you have to Fourier transform it, multiply it with the k-dependent coefficient, and Fourier transform it back. And then you get the EMF. Or you translate your k-dependent coefficients in advance into integral kernels, if that is not too cumbersome, and then work with them in a convolution integral in the original equations, which then turn to be from the differential equations into integral differential equations, because they contain some derivative terms and some other terms which represent the mean EMF, which are convolution integrals. So you would change the nature of your mean field model, but both ways are basically feasible. But it depends more or less on practical aspects what you choose.
So final result should be unique.
I would say yes.
Yeah.
I think there was perhaps an impression that the test field method, in the way that Matthias explained, does not capture the fully nonlinear problem. So because of that, I thought it's useful to consider this simple equation, which is of course nonlinear. And we are going to solve that equation still numerically, but by extracting a linear problem out of that. So we separate the function f into a function that we call fn, and a function that we call fl, for reasons that become clear in a moment. Then the sum of these, by solving the two equations together, we should be solving this equation. Because the sum, if you square this one, you get fn squared twice fn fl, and you get fl squared. Now both equations are still nonlinear. This is nonlinear in fn, this is nonlinear in fl. But we can still solve this equation at the same time. So that means by now we are solving three equations altogether. This is what we call the background turbulence. This is what we call the zero problem.
This is the main run, the first.
The main run, yes. Yes. So this is the main run, and this is the background turbulence, and then this one is the test field equation. But at this point it is still a nonlinear equation. This I can now formulate in such a way that I add one part of fn from here together with one part of fl from here to get this term here. It's still nonlinear. And then in the next step, I can add these two together because that was just fn. So that term is now here. This term is from the one from here. And now the question is this equation linear or nonlinear in fl? No, it's linear in FL.
Oh, because you've got F in there. F contains FL.
But I'm solving this already as a background equation.
Yeah, but if that's a chaotic system, and try it with the Lorentz equations. Try what you've done. Try it with the Lorentz equation. see what happens.
What should we expect? I mean,
Assume you expect numerical noise to separate your two solutions.
You expect not to be able to get a very good growth rate for your linear equation. Depending on where you are on the attractor of the Lorentz equations, you will get a different answer. That's almost the definition of chaos.
Actually, I've been having a problem for a while. That I'm not actually quite certain what we mean by alpha in the nonlinear regime. What can we mean by alpha? There's a work, I guess slightly controversial, Brandenburg, Tilgner, and Hubbard, which showed that if you go to a saturated alpha squared dynamo, then if you just lift that velocity field and put in an out of phase alpha squared field, that the alpha squared, the out of phase field grows. However, if you actually try to put that field into the original equation, that growth is predicted by calculations of alpha. If you put that perturbative field back into the original run, it doesn't behave according to that alpha vector in one time step. Even the first time step, the system treats it as we just shifted the phase and added a little bit of energy to our alpha squared field. We now need to lose that extra little bit of energy. So it's not even clear to me what we actually mean, or what we can mean by alpha in the nonlinear regime. Something I've talked to Matthias. I don't know if he's thought about that at all recently.
maybe he can at least explain to the others what he understands of that.
In that case, you mean the Tegner quantum paper? So,
the question we were discussing under the terms of is alpha a tensor or a scalar?
Yeah, that's a bit an argument between us sometimes. But in summing up, I would say this paper is a good argument for the predictive potential of the test grid method. Even although the coefficient, the alpha tensor, was measured in this case from a saturated state, which is clearly nonlinear. The method would have been predicted, would have predicted that doing this experiment, taking the velocity, treating it kinematically, would result in, occasionally in a growing dynamo. It was known before, but it would have predicted that. Because it can figure out the full tensor, and the full tensor dotted with the right field gives a growing field.
But that growing field is utterly non-physical.
That's another story.
It's no longer related to the system at all.
I accept that, because the representation of the tensor in this form does not play a role in the original system.
So as I would say, I don't see any way we can measure alpha in a nonlinear case.
I mean, it is...
apply that alpha to the original field plus a perturbative field. You have to also get a perturbation to alpha, or something like that.
I mean, I think the solution to the puzzle that you are trying to draw is really that we are not talking about a physical problem here. We are talking about the problem that Steve Tobias and Fausto Cataneo proposed back in Santa Barbara, and the answer to this question we were able to address basically as a kind of lunch discussion during the lunch after Fausto's talk. And so it was a problem of some interest, but it's not one that you find in nature. But it is a problem that is for the cerebral flow field amenable to the mean field approach.
But it just worries me about trying to it says that there's a limit to what we can say about an alpha tensor in a nonlinear case. Because we can only really apply the alpha tensor for the system to a very specific field. And it does not suggest to me that we can't apply it to field plus perturbative field or anything similar, and that makes it very questionable what alpha even means.
But, take a very simple setup. So consider a completely homogeneous and isotropic situation, which we can mimic in numerics. And then kinematically, it's clear that alpha is a scalar, constant everywhere, of course. And now, if there is an alpha squared dynamo, and we let it evolve, and define then the average properly, so that this alpha squared dynamo field is really a mean field, and then not only then, we will already have been observing before that the Beltrami field has a constant modulus. And that for that reason, alpha is, even in the correct situation, still homogeneous. So it, even if the dynamo starts to saturate, it will not change its geometrical behavior. Isn't that true? And you might still model at the end, finally, the alpha effect still by a scalar, which is simply quenched by the modulus of the mean field, and that gives you the amplitude. But at the same time, isn't it true at the same time? Make a question out of that. That because we had no preferred direction before in the system, the only direction which is there now is that of the mean field. And that's why are obliged to formulate the alpha, which is a representative of the properties of the flow, by means of this direction, which is a general construction recipe anyway. Everywhere in mean field theory, we ask for the independent direction in the system and build up the tensors with help of these directions. So if there's a rank 2 tensor, we are simply obliged to write it down as having an isotropic part and another part will have the form dibj. From the point of view that this tensor is describing certain correlation properties of the flow. And if we ask for nothing else, and I think this description is just the proper one. But you are right that the tensorial character of this coefficient disappears later if we dot it with the mean field. Then it falls back to the scalar form. In this specific setup, where the mean field is the only preferred direction. So Steve, you don't accept that?
Well, I accept everything you say about the tensorial representation. Yeah. I think Alex asked a very good question. What does alpha mean in that case, in the nonlinear regime? What does it tell you about? What does it tell you?
Yeah, I understand the point.
And I have lots of discussions about this with Mike Proctor, and we have different opinions. I mean, I can draw something on the board, maybe. Imagine you have a box of MHD turbulence, okay? So I have my box of MHD turbulence, and I calculate alpha from that box. What does it mean? Does it mean that if I put 25 of these boxes together, whatever, 25 exact copies of the boxes together, the MHD turbulence, and I look for the instability of a field that's on a larger scale than my first box, that will give me the growth rate of that field. Is that what alpha means? This is non-linearly saturated.
Sorry?
So each box by itself is non-linearly saturated, okay, and therefore it's forced to be periodic. I calculate alpha just from this box. What does alpha tell me?
So
that's my question to you.
What is the background? The background.
This is MHD turbulence with everything has to be periodic on a scale of this box.
And then you put them together and remove and change the boundary condition.
Right, then I put them together and I say, okay, well, I calculate alpha just on one box. Then I put them together and what happens? Okay, and let's say I introduce a field which is large scale. Okay, so now what happens? What does alpha tell me, or not tell me, about the growth of that field?
Well, the alpha tells you what happens on the scale of the box, right? What happens to a field on the scale of the box?
Telling me about a larger scale field in the box.
No, it cannot.
Yeah, we
If it doesn't tell you anything about the growth of a large scale, why do we calculate it?
Sorry. When we consider a linear problem, we don't speak about any growth rate. Of course, alpha is a function of magnetic field, and total alpha is the sum of dynamic.
Okay, but what do you want to use alpha for? Why are you calculating alpha? Presumably you're calculating
Because we
alpha.
can write simple equation in this situation. You know, we speak
what is
as
that? Sorry.
pure theoreticians. Just a moment. We speak now as pure theoreticians. Of course, it's not a healthy idea. Let's ask, say, Anwar, or even myself, we as physicists, we would like to formulate simple equations in order to understand something.
But what does that equation describing evolution?
Okay, for example, I would like to understand what happens in some stuff. Of course, I can write in such a Bruce style long equation and to produce a lot of beautiful pictures. But answer to real physical answer is not what we find in this way. We should understand mechanics. We should find simple models. If not, we don't understand nothing.
I agree with you. And
So-
I agree in the kinematic regime. I
Not
don't have any
kinematic,
problems.
even non-linear.
Yeah, but I'm asking you, in the non-linear regime, what does alpha describe the evolution of?
Alpha describes,
This situation.
how to say, a way of saturation of my instability. If I know correct alpha, I know how to saturate instability.
So in saturation, total alpha equals 0.
No, critical, critical, not zero. Not critical.
Yeah.
Sorry?
I think the alpha is not enough in this situation. If you add the eta, you get the gradients in the phi, and that helps you to get to the largest scale.
Okay, well, let me ask
I think
this question. Let's say you calculate alpha and eta and everything.
Yes.
Does that tell me about the growth? What will happen next if I add that field? And I can tell you the answer because I've done this calculation. And anybody who's done numerical simulation, let's say you do a numerical simulation and you want to make your box bigger. The first thing you do is you take the smaller box and then you put another box next to it and then you let it evolve, don't you? And so what happens next?
Well, you get information traveling into your neighboring box.
Right, you get, because in this case you've kept a subset of your modes. You've kept, if you have 10 boxes, you've kept the k equals 10, 20, 30. What immediately happens is you get non-linear interactions between the modes, which fill in all the modes in between, right? So if I have my spectrum, and I'm keeping k's 20, 30, 10 from the original thing, and I want to know what happens when I put lots of these boxes together. The first thing that happens is all these modes here grow super exponentially because of non-linear interactions. And then eventually, maybe, the large scale might grow.
Not obvious. Not obvious. If it's real large scale instability, what actually happens? You have got instability in large scale, and this some exponential rate of 10 with magnetic field large scale, nothing else.
These things grow super exponentially. This grows exponentially.
What increased super exponentially? Some small
the
scale
power-
concentration.
Say you take 10 boxes. The mode is 25. The mode 25 here. This mode cannot fit in a smaller box because they're not periodic in a smaller. There are modes which simply cannot fit in the smaller box because they're non-integer modes. And those modes will, I have never done this. I'd always restart the simulation with bigger box. But it's clear that will basically, those modes will fill in on one turnover time. I can't imagine taking much more than one.
But I mean, couldn't you immediately solve this whole problem for the big box? I mean, you should really do that.
You could, but I'm trying to get what information solving it from a small one tells you about the evolution of this large scale field.
I think the answer there is if you assume that you understand the k dependence of alpha, you can reverse engineer things, and probably pretty accurate. That assumes that actual Lorentzian works that well.
Right. The k dependence of alpha, I don't know, I just want to know what does alpha in the non-linear regime? You asked the question. What does alpha in the non-linear regime do?
Alpha tells you what the EMF with the current field does.
I know, but
I don't know. I
change the field.
I know of no evidence that we can, ab initio, take that alpha and have it tell you anything about any other field. However, you can probably run a lot of models, run a lot of simulations, and create a model for how alpha will change. And then you can start using that. But that's a heck of a lot more work.
Okay. Well, if I understand you correctly, I mean, clearly we have to address the problem at the relevant geometry. And learning anything about a smaller box has limited value. It has some value, but perhaps not the one that we really want to have at this minute.
I think the key point is that the alpha in the small box stems from a gradient within that box, right? And if you have a gradient that goes down, then you end up with a zigzag potential, which is maybe physically
that's crazy.
Not bad. So the alpha encapsulates flow gradients in homogeneities and that sort of thing. So
but I mean, what we have learned from non-locality, we know this alpha tangent is an integral kernel.
Yeah.
And so therefore, we have to learn what the structure is for a given representation of turbulence. So therefore, we may not need to actually solve for the full system, but we have to know what this kernel is and use the relevant experiments to figure that one out. And once we know this, we have to apply that to the relevant geometry.
But I'm assuming you can calculate alpha correctly, precisely correctly in your small box. All I'm asking is, what would that mean in the non-linear regime? That's all. That's the same question that
I can only add one aspect to it. So we have all the while have been speaking about alpha, and this is clearly not sufficient. And I've made here an example. If we assume, if we make very simplifying assumptions, which I have shown here, and the most important is maybe. Oh, what's that one? And especially these here, that's higher order spatial and temporal derivatives of B are negligible, and that the current entities in some sense weak, which is of course not clearly to be qualified. Let us assume that. And then finally it comes to the point that we really, as you said, are interested in the mean EMF, not in some enigmatic coefficients. And if you first start with a notation using the coefficients, but then boil this down to a final form where we would have only a minimum number of independent functions, then we come to this form, which has the property, as I said, that it is just linear in the modulus of J. And as long as we don't know these in total 5 functions, 1, 2, 3, 4, 5 in red, I think we have no chance to provide a predictive model.
Okay, but if you've got those exactly right, let me say you've got those exactly right in your from the calculation on your small box.
Right. Yeah.
What does that tell you about the calculation?
I understand that it's another aspect, but I guess the hint is correct that if we could learn at the same time with this nonlinearity correctly about the non-locality, and at the moment I don't know how, but this is what we need to know. If we learn from the small box correct about the non-locality, then I would say then we're indeed able to predict the behavior over many boxes. But not without this information.
You have to be able to predict the super exponential growth of all the modes that are going on.
Okay.
I don't know how you do that.
I cannot answer that.
Super exponential growth without aid.
No.
Until end of universe.
It's saturated.
Okay. It is
When I start off with a spectrum,
what's the typical time of saturation? Steve, what's the typical time of saturation compared with external?
Very fast.
Very fast.
Within one turnover time.
Very nice. It means that I can define this effective coefficients after saturation.
But you've saturated in a state different from the one that you started off with when you calculated alpha for.
But, right.
Okay. In principle, we can understand the process of saturation just introducing nonlinear diagonal number and as a, for example, if we have alpha squared diagonal in the beginning, okay? So we have here alpha as a function of time and b divided by square divided by eta t square multiplied by some scale. Okay? So in principle, here we have saturation total alpha, which is the sum of kinetic plus magnetic, should tends to 0. Yes, and sorry. Okay, well, let me finish.
But there's turbulent diffusion.
Sorry.
There's turbulent diffusion still.
Yeah. There is turbulent diffusion, but there is a balance between alpha generated term and in steady state. In steady state.
Steady state is the balance between the alpha term, the eta term, and the eta resistor.
Yes. Exactly. Okay. Well, let's consider larger number.
And then the balance.
Yeah. Of course, this value also can depend on V. This is depend on V, and total alpha is total alpha is the dynamic part which depends on V plus V. Dynamic part and plus magnetic part, which depends explicitly on time. Depends on time and B, but even at saturation state, total alpha should tend to critical value.
Critical value where D is 1.
Sorry?
If you're putting D to 1, then I'm happy. D goes to 1 in the saturated case. Not 0.
Okay. D tends to D critical.
Yes.
Yeah, of course. Yes. That's why, so if we calculate functional derivative of electromotive force in the function of B, so it yields us total alpha. These two.
That's not what the test field provides.
And so this yields some diagnostics.
That'd be very
For orientation. I understand that numerically it's not easy to do.
Okay, that is in some sense the ideal definition for alpha.
Yeah.
And that is not what I think any of the current alpha measuring techniques provide.
Okay, because
should be improved technical.
Yes.
If it's not according to the definition.
Yes.
Actually, Alexander, it's your problem, not ours.
No, it's also our
No, for the job.
But but this is important information about the system, how nonlinear dynamo number behaves.
Yes.
And that's why we need this diagnosis.
So
Right?
I guess
Well,
my question of what you get from the alpha stems from the fact that what we can measure currently with our current technology is not that functional derivative.
Yeah, of course, because up to now only kinematic test field is developed. Okay, but the next step, developing of nonlinear test field method. And one of the ways calculate in some way, determine in some way functional derivatives of electromotive force. And then it will be a very powerful instrument for diagnostics. That's why we need alpha.
And of course, the way how to find non-localized.
Yeah,
because it's not, it's how to say, confused with this conception of non-local alpha effect.
But it will be very useful information about the system.
Okay, so
Okay, this is a dream of theoreticians.
No.
yes, I think we should move on to different subjects. This is getting quite vigorous, and maybe not everybody is so well into this subject. And one of the things that was brought up early this week was several dynamo experiments, and then the issue that they might have been prematurely closed down or dismantled. And I was wondering if Axel was one of the people who was making this point early on, so would you like to elaborate on that?
I don't think I made this point up, but I think somebody else made it up and I noted it down. But who brought this up, this point? Don't dismantle the experiment too early. It was you. Yes, and I fully agree with you. And we are talking about, for example, there is of course you were talking about Karlsruhe, and I was talking about the Newcastle experiment. In both cases, things were overlooked.
Yeah, I just can reiterate, so it turned out that the Karlsruhe experiment was shut down in 2003, I guess, after we provided plenty of data. That's very fine. And then a new director came up and he had to stop everything. It was not the intention of Robert Stieglitz to close it, but later it turned out that we could have done something more with changing some boundary conditions, changing some flow profiles in order to get maybe an axial dipole and maybe even transitions, reverses between axial and equatorial dipoles. So this is my conclusion. So if you have a running dynamo, don't shut it down too early and wait for the opinion of theoreticians. Okay, that's it.
And, I would like to know the state of the art concerning the opinion about the VKS experiment. So in VKS experiment, after people started to use iron impellers, then it's allowed to decrease threshold in excitation of dynamo. But there was a large discussion about is it really dynamo, or what is the role of these iron impellers, and is it only we decrease only threshold for generation of the magnetic alloys, some artificial dynamo, what we have?
I think from what Andre has published in the PRL recently and in a new JFD paper, I think it's quite clear that the high permeability, which is around 7 T in this disk, is extremely important. So it does not just decrease the critical Rn, but it changes the topology of the flow of the ion field completely. So yes. Sorry, of the flow, of the field, yes. So it's now we see that it's mainly a strongly dominated toroidal field, and which is more or less axisymmetric with some wigglings and fluctuations around this. So this was not predicted by theory before, so we expected to have an m=1 mode, which is with a critical Rm of 50, and now we see an m=0 mode with a critical Rm of 30. This makes a big difference. And it turned out from the simulation, including the high mu effect, that this high mu plays an absolutely essential role for the dynamo. The nice thing with this is that you have, this is our opinion at least, that you have two separated dynamos at each of the propellers one. And the nice thing with this is, so you have two dipoles, and they can add either constructively to a global dipole, or they can subtract to a quadrupole. And this allows you to have a very complex dynamics when you are playing with rotation rates. And this is, of course, the big advantage of the VKS experiment, that they get fantastically dynamical effects between different things, reverses, and don't ask me everything. But the reason is that you don't have a homogeneous dynamo, but two separated ones, which are dominated by the high mu. This is at least our opinion, which can be justified by numerical simulation.
One comment to that. One reason why we believe that, and Jean-François Pinton believes that too, is that these dynamics, these reversals or these oscillations, they vanish if one of the flow driving impellers is made of stainless steel. So if only one impeller is of soft iron and the other is of stainless steel, then all these dynamics vanish in the experiment.
There is no any dynamo?
There is a dynamo if at least one impeller is made of soft iron, you still have a dynamo, but then you don't have all these dynamical features like bursts, reversals, oscillations. They are only there if you have two impellers of soft iron, and and they rotate with different frequencies. But both of them must be of soft iron if you want to have these dynamics. And that's the reason why we believe that we have two different interacting dynamics.
But maybe I can add something about the... So I wasn't there on Monday, so I don't know if you are aware of the new test that the VKS team tried this year. They tried to keep the disc with soft iron, and they replaced the blade by copper, and this is one test. Another test was to have a copper disc and blades with soft iron, and in both cases the dynamo did not work. So,
but this is another issue, so
yes,
both of them must be of soft iron.
Yeah, so it means that maybe the reality is more complex, and then we, as Igor said, we can wonder if it is a dynamo at all, because you know that some seed magnetic field exists in the soft iron discs and in the plates, and so I know that they try to get rid of this uncertainty, but so far it remains in the minds at least.
I would think it is a dynamo, but not a homogeneous one.
Okay, this is your opinion, and
But
I respect it.
They never absorbed kinematic stage. They absorbed only non-linear stage of this dynamo. They can not measure growth rate of this dynamo stability.
Is that true?
At least for high power.
It would be strange. Is it true? That they cannot measure the growth rate.
But I don't know, what do you mean by the growth rate? They see an increase of the magnetic field and then a saturation. So which would correspond to a kinematic regime and a saturated regime.
At least I asked Jean-François 2 years ago. He said me that they never absorbed kinematic stage and they said exponential growth of it.
Instead?
Yeah?
Instead what?
They absorb
Yeah, but there must be a growth rate.
It must be growth rate.
But what is this like? If it is not exponential, what is it like?
I think there is an exponential. But you never know if it is an amplifier or a dynamo. This is the point, you see. And the only way to be sure would be to get rid of these ferromagnetic materials.
We already were. And second, still in the same place.
And so they are trying hard to do it, you know.
But if it's true what Frank said about the impellers, how different is this dynamo from the Lowe's-Wilkinson experiment? Seems very similar to me.
You mean to rotators?
Yeah, because you've got two rotators and.
The difference is if you don't have any sodium, you probably don't have any
well, obviously you need something to make electrical contact, but that's a bit different from it being a fluid dynamo, isn't it? It's a kind of dynamo in the discs, which are kind of coupled by the fluid. That's slightly different.
The Kalarash experiment really seems to be a mean-field dynamo, because it produces a magnetic field which is not compatible with Coulomb theory, if you just use the average motions. So it's really the U cross B toroidally average which does the dynamo. So this was well known, right? Some comment on that? I mean, Steve was asking, is there a difference, if I understand you correctly, between the Kalarash experiment and the Lawrence-Wilkinson experiment? And of course, Lawrence-Wilkinson is manifestly a laminar dynamo, a slow dynamo.
that can be described by without any averaging if you just take the actual velocity field. If you took the velocity field of the two rotors in the Kalaraj experiment and use just the mean flows that you get from that and the induction from those mean flows, then you should get a non-axisymmetric magnetic field, which is not what you get. You get an axisymmetric magnetic field.
Yeah, and this is a turbulent dynamo because there is very strong turbulence there.
Yeah,
we must now with 10 to the 6.
You can't call it turbulent dynamo if it's not dynamo.
If it's not a dynamo,
there's
yes.
something there which is there because of the colours, and then there's turbulence in between. That's not the same thing.
But unless you have some alpha effect due to the blades. In this case, you recover some axisymmetric magnetic field.
And it's not, I don't know what is the induction mechanism, it doesn't need to be alpha, there's others which can produce large-scale fields.
Axel, I can comment on your remark. There's a paper by Christoph Sochi, and he showed that in simulations he gets first an m equal 1 mode, and this then drives a flow component which needs to be axisymmetric field. So to your objection that it should be a non-axisymmetric field, just taking the mean flow components of a current flow. So this is bypassing this counting theorem. This is I think also the title of the paper.
But Martin, this is really theoretical because in this case you would need such a high magnetic field coming from the m equal 1, which is not realistic. So I'm quite sure. Let me say a point about this mean field character. So what we see, these high magnetic field propellers they produce, they prefer strongly the toroidal mode, but they alone cannot give a positive growth rate. So you're slightly below the zero, and then you need a little bit of alpha or whatever to get it over the zero line of the growth rate. And so it's a very complicated mechanism. You have this omega effect and this special effect from the nu, from the boundary conditions and from the high magnetic permeability, but you still need a little bit of alpha to get the dynamo running in this acceleration. This is in Andre's paper.
In this system there is a very strong shear. So, and turbulence is inhomogeneous. It's obvious that in such system should be non-zero alpha. Generated of, there is some generation of helicity coming plus in this system. Of course we have two rotated system in the opposite direction, but nevertheless in every part of this system we should generate alpha effect. By shear and by inhomogeneous.
This is the idea of Stefan Vogt and Font and so on, that you have the 8 blades, and between the 8 blades you have the outflow coming out. And this might have a helicity, and this helicity is something like coming from the 8 blades which are coming. This is at least an idea.
I've got a funny idea. Let's use a new system, test field method. What does it mean? Impose additional magnetic field, very weak, and measure electromotive force. Maybe it's possible. Or something what happened in this situation.
Does our spiritual father, Karl-Heinz, have something to say on this?
No.
No?
Why is it possible?
No, it's difficult to measure, we measure magnetic field in 2 points, I think, as far as I understand.
You don't need any more.
Yeah, so the velocity field cannot be measured from real experiment. Only in both experiments in such system. So it's difficult to perform any measurements of electromotive force.
Maybe not electromotive force, maybe current, who knows, but something with, because it's a very, I would say, good idea to use some magnetic field.
Concerning the VKS experiment again, it seems that the turbulence is not at the origin of the dynamo action.
Really?
Why?
Why?
Because well, the only way we have to explain it is what you have done, what I have done, which relies on maybe some existence of large scale, mesoscale between the turbulence scale and the scale of the device. So, for example, the scale given by the blades, the 8 blades, or equivalent fluctuation in the mid-plane. But it is not the small-scale turbulence we would expect from, I don't know, midfield and so on.
Reynolds number 10 to the 6th power. Of course, this Reynolds number is based on the angular velocity and the size of the system, but if you decrease this number by 2 order of magnitude, so consider that fluctuations is about 10% of mean velocity, and the correlation length is 10% of the size of the system. Now, 10 to the 4th power in nodes is a huge.
Is it true? Is it really such high?
Yeah, but according to estimates, their estimates Reynolds number 10 to the 6th. Peter, is it true?
Yes. Yes, 10 to the 6 is not a big number.
It's a huge number. It's developed turbulence.
Of course, there is turbulence, but what I say is that the dynamo, I mean the magnetic Reynolds number is very small, even if the Reynolds number is large.
Yeah, magnetic Reynolds number is about 10. If
it's
about
about
10 to the minus 5, so magnetic Reynolds number is 10. So really, magnetic Reynolds number based on the different characteristics is small. Yes.
Okay, maybe this is...
but one further comment maybe for Frank, because he is about to build a new experiment. When we look at all the dynamo experiments which have been built so far, so the Riga experiment, the VKS experiment, the Karlsruhe experiment, in fact, it seems that only the Karlsruhe experiment started from forcing at small scale compared to the scale of the device, and maybe this is something which could be done in another way to try to have a forcing at small scale and not always the forcing at large scale. Of course, it is easier to inject energy and power in the fluid at large scale, but maybe it would change.
Okay, maybe this is a good time to end our proceedings for today and continue these interesting discussions during the dinner. So let's... and the dinner is at 7 o'clock.
7 o'clock is the dinner.
7?
Yeah. 7 o'clock. Yes, this is a number just for emergency cases. You can imagine I'm not exactly keen in taking much course during such a time. And the Toastmaster of tonight will be Anwar. So please don't do anything else without him.
That's not the point.